Hi, I'm Maurice Dupre, and in this section we're going to discuss trigonometric integrals. Let's begin where our integrands are products of sines and cosines. Here, I want to compute the indefinite integral of sine to the mx times cosine to the nth power of x dx. To begin, suppose at least one of those two powers, m or n, is odd. In that case, we can use the cosine squared x plus sine squared x equals 1 to get the integral in the form of polynomial in sine x times cosine x dx, or integral polynomial in cosine of x dx times sine x dx for some polynomial p. Of course, if both m and n are even, we'll use these double angle formulas to simply reduce the powers by half. Of course, you'll get big algebraic expressions to multiply out, but you keep reducing the powers by half until you have at least one odd power. Well, the best way to see how this works is with an example. And so let's look at our first example. The integral from 0 to pi over 2 of sine to the 5th power of x dx. And so we begin by writing that as the definite integral from 0 to pi over 2 of sine to the 4th x times sine x dx. We peel off one power. And now with this 4th power of sine of x, I can actually write that as a power of sine squared. Notice in this case that sine squared of x simply squared. Now we use our Pythagorean identity. Sine squared of x is 1 minus cosine square. So we have the definite integral from 0 to pi over 2, 1 minus cosine squared x, quantity squared, times sine x dx. And you see at this point we can use substitution. We're going to substitute u equals cosine x. Then du is simply negative sine x dx. And so consequently, sine x dx is negative du, which will come outside the integral. We have negative of the integral, and now let's change our limits. When x is 0, u is cosine of 0, cosine 0 is 1. When x is pi over 2, u is cosine pi over 2, which is 0. And then we have 1 minus the quantity u squared, and that's all squared, times du. And so after substitution, our integral has simplified completely to the problem of integrating a polynomial. Of course, negative integral from 1 to 0 is the integral from 0 to 1, and we need to square this polynomial. The square of 1 minus u square, of course, that's the same as the square of u square minus 1, would be u to the 4th minus 2u square plus 1. And so consequently, this is now an easy application of the power rule for antidifferentiation. We have u to the 5th over 5 minus 2 u cubed over 3 plus u to be evaluated from 0 to 1. We get 1/5 minus 2/3 plus 1, and that is simply 8/15. Let's look at an example of a definite integral of an odd power of cosine of x now. Here, I want to compute the definite integral from negative pi over 2 to pi over 2 of cosine cubed of x. So we'll begin by simply peeling off the highest even power we can find there. That would be cosine squared. So we have cosine squared x times a single factor of cosine x. And now with this cosine squared of x, we can replace that by 1 minus sine squared of x. So we have 1 minus sine squared x multiplied by cosine of x dx. Well, notice I can now do the substitution u equals sine x, for then du is cosine x dx. And so here's du, 1 minus u squared du. Well, let's change our limits. We're substituting u equals sine x. When x is negative pi over 2, sine of negative pi over 2 is negative 1. When x is positive pi over 2, sine of plus pi over 2 is plus 1. So we're now integrating from negative 1 to 1, 1 minus u squared du. So we have 1 minus u squared du. Well, that's certainly an easy integral to compute. Just use the power rule for anti-differentiation. We have u minus u cubed over 3 to be evaluated between limits negative 1 and 1. Of course, when I put in plus 1 for u, I get 1 minus a third. Now we subtract what we get by putting in negative 1. That's negative 1 minus negative 1 cubed is negative 1/3. You have to be careful with all these negative signs here. Well, negative 1 minus a minus is plus. Negative 1 plus a third is negative 2/3. Negative negative 2/3 is plus 2/3. On the other hand, 1 minus a third is 2/3, so we have 2 times 2/3. A 2/3 for each term. And so consequently, we end up with 4/3. Now, one thing you can notice here, which would simplify the work, especially in dealing with all these negative signs, the cosine function itself is an even function. And so whenever you integrate it from negative a to plus a, that will be twice what you get by integrating 0 to a. And so consequently, that would mean we know in the end we're just going to get what we get by putting in the upper limit and doubling it. The 2 times 2/3 is 4/3. Well, now let's look to see what happens when we only have an even power. Of course, you must remember to use the double angle formulas to reduce the powers then. Here, I have the definite integral from 0 to pi of 8 times sine to the 4th power of x dx. So our previous technique will not work. In this case, what I want to do is use the double angle formula, which says sine squared of x is 1 minus cosine 2x divided by 2. And so now we have integral from 0 to pi. I'll pull the 8 out. Sine to the 4th, well, that's sine squared quantity squared, so we have 1 minus cosine of 2x all divided by 2, and that quantity is squared. So now 2 squared in the denominator comes out as a 4 in the denominator. 8/4 is 2, so we have twice the integral from 0 to pi of the square of this numerator. 1 squared is 1, minus the cross term would be minus 2 cosine 2x, and then plus the square of the cosine term itself, so that'll be cosine squared 2x, all dx. And notice we can easily do this integral, but here I've got another even power of a sine or a cosine. In this case, I have cosine squared 2x. And so now I will use the double angle formula for cosine that says cosine squared of any angle theta is equal to 1 plus cosine 2 theta all divided by 2. So we're going to apply that with theta being 2x, and so 2 theta will be 4x. And so now we have twice the integral from 0 to pi of 1 minus 2 cosine of 2x plus 1 plus cosine of 4x now, all divided by 2 dx. Well, we've got a lot of cosines to integrate here, but look what's going to happen. As cosine of 2x, with x varying from 0 to pi, 2x will vary from 0 to 2 pi. So we're actually integrating over an entire cycle of cosine here from 0. In other words, the entire thing's going to cancel out. 4x integrated from 0 to 4 to 2 to pi goes through 2 whole cycles of cosine, so that integral will be 0. The only thing that's going to contribute is the 1 and the 1/2. So we'll have integral from 0 to pi of 1 plus a half dx, which is 3/2 times 2 is 3, integrating from 0 to pi, simply 3 pi. Well, always keep in mind the double angle formulas when you're dealing with these indefinite or definite integrals involving sines and cosines. Let's look at an example. Here I want to do the definite integral from 0 to 2 pi of the square root of the quantity 1 minus cosine x all over 2. Well, remember, sine squared of x is equal to 1 minus cosine of 2x all divided by 2. So consequently, if I see 1 minus cosine x, if there's only an x here, then I can get the formula to give me sine squared of 1/2 x. So if I cross off this 2, sine squared 1/2 x is 1 minus cosine x over 2. Well, let's write that clearly now. Sine squared of 1/2 x is 1 minus cosine x all over 2. So we'll simply use this substitution for the quantity in the radical. So this integral then becomes the integral from 0 to 2 pi of the square root of sine squared of the quantity 1/2 x dx. Now, whenever you take the square root of a square, you are getting the absolute value. So we have the integral from 0 to 2 pi of the absolute value of sine of 1/2 x dx. Well, let's begin by getting rid of the 1/2 here using substitution. We'll substitute u equals x over 2. Then du is simply 1/2 dx. And so consequently, dx is 2 du. And so when we make the substitution, then we'll get integral of absolute value of sine u times 2 du. Well, we'll put the 2 out front. And now let's fix our limits. When x is 0, x over 2, 0 over 2 is still 0. But when x is 2 pi, u is 2 pi over 2, which is simply pi. So now we're doing the definite integral from 0 to pi of absolute value sine u du. Well, recall the graph of sine x over the interval from 0 to pi is simply the first half of the sine wave. It's above the x-axis the whole time, and so consequently it is always positive. So consequently I can now drop the absolute value. I don't have to worry about it. So we're just doing the definite integral from 0 to pi of sine u du. And then we're going to multiply the result by 2. Well, let's do that. Let's write that down integral from 0 to pi multiplied by 2 sine u du. What's an antiderivative of sine u? Well, that's simply the negative of cosine u. And we're evaluating between limits 0 and pi. Well, the cosine of pi is -1. The cosine of 0 is +1. So we'll have 2 times negative cosine pi, that's -1, minus the negative of cosine of 0, which is 1. You have to be careful with these minus signs, but look what we have. Negative, negative, positive. Positive 1, negative, negative, another positive 1. So we have 2 times 2 is simply 4. Now let's look at an example involving secant. For instance, if you had powers of cosine in the denominator by itself, then you could turn those into powers of secant. Here I want to compute the definite integral from 0 to pi over 4 of secant to the 4th power of theta. So what we do here is remember that secant squared is 1 plus tangent squared theta. As well, the derivative of tangent is secant squared. So we can use this in this little trick by writing the integrand as simply secant square theta times secant square theta. Now the first factor of secant square we'll rewrite as 1 plus tangent square theta, and then we'll do the substitution u equals tan theta, and here will be the du sitting right there. So consequently we have integral 0 to pi over 4, 1 plus tangent square theta times secant square theta d theta. We'll substitute u equals tan theta. Then du is the secant square theta d theta. And so consequently, I'll just have the integral 1 plus u square du. What are our limits? When theta is 0, tangent of 0 is 0, so u is 0. U, when theta is 0, is the tangent of 0, which is simply 0. When theta is pi over 4, tangent of pi over 4, remember pi over 4 is just that 45-degree angle, so there's a little picture. There's the pi over 4 angle. Tangent opposite over the adjacent is 1. So when theta equals pi over 4, u equals 1. And so look how simple our integral has become. Now we can simply anti-differentiate using the power rule. We have u plus u cubed divided by 3 to be evaluated between limits 0 and 1. So all I have to do is put the 1 in. We get 1 plus a third, which is 4/3 for the final answer. Well, we don't always have just products and powers of sine x and cosine x and tangent x and secant x and so forth. What do we do if we had, say, sine 7x and cosine 8x and things like that? Well, let's look at some formulas for simplifying those. If I have sine of mx multiplied by sine of nx, that can be simplified to 1/2 the cosine of the quantity m minus n times x minus the cosine of m plus n times x. If I have the sine of m of x, the sine of mx times the cosine of nx, that can be simplified as 1/2 the sine of m minus n times x plus the sine of m plus n times x. If I have the cosine of mx times the cosine nx, that's 1/2 the quantity cosine of m minus nx plus the cosine of the quantity m plus n times x. It looks like it might be difficult to remember these, but it's not so bad. You may have noticed from the addition formulas for sine and cosine that the sine tends to mix things. When I have the sine and the cosine mixed, I get sines. When I have only sines, I get cosines. When I have only cosines, I get cosines. When both of them are sines, we have the difference, whereas when both are cosines, we have plus. In fact, the only one that has the difference here is when both are sines. So when I have sine of mx times sine nx, it will be cosine of the difference of m and n times x minus the cosine of m plus nx. Does it matter which one we think of as the first factor? No, because cosine is an even function. So cosine of m minus n times x is exactly the same as the cosine of the quantity n minus m times x. In the case of the product of cosines, notice we have those exact same two terms except with a plus sign. So let's look at an example where we apply these formulas. Here, I want to do the definite integral from 0 to pi of the quantity cosine 3x times the quantity cosine 4x. And so what we see is from our formulas, that's 1/2 the integral from 0 to pi of, it's the cosine first of the difference. Take the bigger and subtract the smaller. 4 minus 3 is 1, so we just get cosine x plus the cosine of what we get by adding the two coefficients. 3 plus 4 will be 7x. Well, that's not so bad now, is it? Antiderivative of cosine x is simply sine x. So we have 1/2 sine x to be evaluated from 0 to pi, plus 1/2 the antiderivative of cosine 7x. Well, that's sine of 7x divided by 7, also to be evaluated from 0 to pi. Well, sine of pi is 0, sine of 0 is 0, and sine of 7 pi is 0, sine of 0 is 0. So everything just ends up being 0. We get a great big 0 here. Well, let's look at an example where we have an integrand which mixes sines and cosines now. To review from our formulas that are useful here, in this case we want to remember sine of mx times cosine nx is 1/2 the sine of m minus n times x plus the sine of m plus n times x. That is, notice we have sines both times connected with the plus. The only thing we're going to be doing is subtracting the cosine coefficient from the sine coefficient here. Remember, that's the order. M minus n, where m is in front of the x in the sine function and n is in front of the x in the cosine function. So with that in mind, let's look at this example. Here I want to do the definite integral from negative pi to 0 of sine of 3x times cosine of 2x. And so consequently, that will equal 1/2 the definite integral from negative pi to 0. Now remember, both terms involve sine. I begin by taking sine of the sine coefficient minus the cosine coefficient. 3 minus 2 is 1, so I'll have sine of x, and then plus the sine, what I get by adding the two coefficients. 3 plus 2 is 5x. Well, that is an easy integral to do, and what I will do is say that is 1/2 times the negative of the integral from 0 to negative pi, and put the negative sign inside the integral. So I have negative sine x minus sine of 5x. Now, the derivative of cosine x is negative sine x, so each term has antiderivative as a cosine function. We have 1/2. Antiderivative of negative sine x is cosine x. Antiderivative of negative sine 5x is cosine of 5x over 5. That's to be evaluated from 0 to negative pi. Well, you might notice here that cosine is an even function, so it doesn't matter whether I have negative pi or plus pi up here. And so the key thing here is, what is the cosine of negative pi or pi? It's negative 1. Likewise, in the case of 5 pi, odd multiples of pi are going to give negative 1. And so consequently, what I will have here is, when I put in the plus or minus pi, I will get the negative of 1/2 times 1 plus 1/5. And then I will subtract what I get by putting in the 0. Well, that's simply, cosine 0 is 1, so we get 1 plus 1/5 again. So notice both terms are negative. Of course, we have to remember the 1/2 out front. Each is multiplied by 1/2. So we have negative 6/5 times 1/2 minus 6/5 times 1/2. Added up, that's just negative 6/5. Well, we've worked some problems involving trigonometric integrals. Remember, when you see products and powers of sines and cosines, if at least one of those are odd, then you're okay. Just use the Pythagorean identity, cosine square plus sine square equals 1 to simplify. Likewise, when you see even powers of secant, you can use 1 plus tangent square equals secant squared, and the fact that the derivative of tangent is secant squared. Well, check these formulas over and practice with them so that you can do trigonometric integrals. Now that you've seen these, you should try some on your own.